Okay, so I've been looking at the holographic principle, which Gabor discovered in 1947. He won the Nobel Prize with this paper here, the basic idea of holography. Okay. Now, how does the relativistic slide rule fit onto that? Well, if I take that image above and sort of distort it so that it fits onto the relativistic slide rule at a b value of 0.6, which is my favorite one, then this that point becomes point B, and this point here becomes point A. So point A is where the reference wave comes from, and basically it hits the object, and then you get an object wave, and then when it hits the photographic plate, which is this line along the top of the little circles, it interferes, and because of the phase differences, then that just gets locked in as the whatever the medium is that the holographic plate's made out of, that just locks it in, goes solid or whatever, and so it's locked in on the plate there, all that. So with a normal photo it's just intensity, but with a hologram it records the phase differences as well. So that's, and then what you get is somebody observing the so then you take this object B away, and then you turn on your light A again, and it goes through the holographic plate, and this time it can only get out, ricochets its way through, and comes out at all these angles. And then when you're observing the light that's coming out of that plate, you observe, and the image has been taken away. I mean, the object's been taken away now, but you observe it still to be there, just by inferring that it must still be there because of the photons that are going into your left and right eye. Okay, so that's that principle, and now I've come up with the I think I've discovered Schrodinger's equation, which is a matter wave. But let me just start by introducing the normal light wave equation. So this would be 360 over L, and that'll give me the wavelength. See there, it's 0.8, so those crests are 0.8 away from each other, so that's the wavelength. Notice that it's 1 over L, not L. And then to get the period, notice it's 1 over T. And so here, that's T, isn't it? 1 at a B value of 0.6, T is 1.3 recurring. So it gives me the distance between the crests is in time. So it's period. The period is the distance. And I did try to, you can just add them together. You don't normally do that, but I can do what I want with the relativistic slide rule, and that gives me a parallel redshift. And I don't really need the waves, the wiggly bits. I can just add them together without the cosine, and I get 2. So let me just show it here, zoom out a bit, you can see that that's 0 there. That's 4 there. Oh, that's 2 there. Let me go to a higher B value. You can see that these beat frequencies really start to appear now. So at 0.8 you can see that the parallel redshift is 3, and that's the distance between the beat frequencies. So anyway, that's obviously not the wave function. Schrodinger's equation is obviously so what is T over L squared? Well, it's obviously inverted, going to be inverted. So this is just me hypothesizing as to what Schrodinger's equation would be according to the relativistic slide rule. So you can say that it's L squared over T, which is Planck constant over the mass, which is obviously in the Schrodinger's equation. So let's have a look at that. So that would seem to be Schrodinger's equation, which is 2 times Planck's constant, that distance from there to there, over to, it's called specific, it's a specific value, but I found that if I take the modulus and square it, which is the Born rule, which normally gives you a probability density function, then you get this wave. And let me go to back to my 0.6. And if you look at this probability density function, you can see that it's popping its head out above the photographic plate by 0.28, and 0.28 is little b. The little b is actually the length of this the length of the distance between. You can see that little opening there. There's a distance, that's little b. It's the same as that. And then if I take the modulus of that and square it, I get the intensity of photon reflection, which is this little dotted thing coming up. It's the reflected part. If you were to have a surface here, and then a photon was to hit that surface, this is always Bruce's angle, so that's the transmitted light, and that's the S-polarized light, 100% S-polarized light that reflects off this surface. So you can imagine that this is a photographic plate, and this is the reference wave, and it's going through the photographic plate, and it's hitting it on that angle and going through. And then if you have like a sine wave type slits, then you only get your 0 and your 1 value of m. You don't have to worry about the other ones, and that's why I put that guy looking like that, because he's only going to see m equals 1, which is those dashed lines going up the side of the red wave, which is a probability density function. So that all looks pretty good. And then I'm imagining that collapse of the wave function. When that happens, let me just put in the anyons. So I've got a red anyon, a green, and a blue anyon, and then when b equals 1, it's completely in a superposition. And so that's like a boson or a photon. But then when it collapses to a spinor, it collapses again, but this time went to b equals 0, and this time the superposition separates out into the picture I've got there of a spinor. So I've got a picture here of a spinor. That one is a picture of a spinor, and so that superposition is just separated out. Yeah, due to superposition collapse, I've put there, and antimatter, matter-antimatter separation. I haven't animated this properly, but I can imagine that that spinor is collapsing into a superposition like that, and now it's gone. So it's a boson. And then as it collapses again, you get a fermion there, separated. Notice with the wave function, Schrodinger's equation, and the probability density function is the 4 there. Don't know why it has to be there. It's something to do with general relativity, maybe. This is the thing about trying to produce a theory of everything when you don't really know much about physics, is you're sort of a jack of all trades, a master of none. You're just trying to get sort of like put together an overall picture without really understanding anything very well. It's the way it is, for me anyway.